I need to ask, who's got the plastic fly? Here we go, here we go. There we go. All right. Hi, everyone, and welcome to our live stream. I'm Danielle from Blackrock Observatory, and tonight we'll be having a chat about the recent discovery that was announced through the publication that happened in Nature about phosphine, because it was detected in the atmosphere in Venus. And I am, hold on, I just want to mute this here. There we go. There we go. So I don't want to say too much about the discovery because actually we have a bunch of experts here. So I'm actually going to turn that over to them in just a minute. But I just want to start by saying happy Space Week. Welcome to the YouTube channel. And if it's your first time here, make sure that you hit the subscribe button, because when you do that, then you get notified about the next time we do these lives and you won't miss out. Basically, you'll be able to join in and have conversation with us. So we'll have a live chat happening here as well on the YouTube channel. So join in the conversation, put your questions there, anything that you might want to ask our experts, and we'll do our very best to try to answer as many of those questions for you tonight. So let me go ahead and introduce the group here. I have Dr. Niall Smith, who is an experimental physicist and astrophysicist and head of research at the Institute of Technology, and has written about the possibility of the existence of life in the universe. And I have Frances McCarthy, who is our education officer at Blackrock Observatory, and she is also a huge Venus fan as well. And I have special guest Dr. Eamonn Culligan, and he has it's Culligan, right? And I said, I'm sorry, Eamonn. I asked you in advance too, and I still said Culligan. But his background is in biotechnology and microbiology, and has a specific research in synthetic biology and bacterial stress responses, which I think will be pretty important for the conversation that we're going to be having tonight. So I just want to go ahead and jump right into the announcement. Let's talk about phosphine. What does it mean? And I'm going to turn it right over to you, Eamonn, and tell us a little bit about phosphine. What is it? Why is it important that we've found it in the atmosphere in Venus?
Thanks, Danielle. So for me, I mean, phosphine, or the story of finding phosphine on Venus was quite interesting, and I hadn't heard of phosphine before this story happened. So I've kind of just been reading up a little bit about it recently, and it's a gas. The chemical formula is pH3. So it appears to be quite a volatile gas, very toxic, quite flammable. But I think the significance of it, the significance of finding phosphine in the atmosphere of Venus, seems to be that the energy to create phosphine wouldn't seem to be present on Venus itself. So one of the explanations possibly is that, you know, an alien life form, possibly, or a microbial life form, is actually forming the phosphine in the clouds around Venus, and that could be a possible explanation for it. I think another explanation possibly is that there is some sort of unusual chemistry going on in the clouds around Venus. And again, you know, either way, whether it's microbially derived phosphine, or whether it's some sort of novel chemical process, I think either explanation is quite interesting.
So because this is on Venus and it's such an extreme environment, you have a background in extremophiles as well, right, Eamonn?
I have, my main interest would be in bacterial stress responses, and that goes back a long time when I was doing my undergraduate project in University College Cork, where I was studying kind of bacterial stress responses in non-extremophiles, and the stress responses in those bacteria would be over quite a narrow range. But reading broadly around that topic, you would kind of, or I kind of came across the idea of these extremophiles, these bacteria and other microbial organisms that live on Earth, that really live at the extremes of temperature and pressure and pH and things like that. So that's kind of where my interest came from, was kind of these more narrower stress responses. But then there's a much broader range of stress responses in these microorganisms that actually live on Earth. And I suppose in relation to other planets, that the levels of tolerance to these extreme stresses that these bacteria have would be somewhat similar to maybe some of the conditions that exist on some of these other planets.
Okay, so can I just jump and ask a question here? Because
Please, yeah.
Venus is great. I mean, Venus fan here. Not so much the surface of Venus on the kind of hot cooker, you're dead if you're on the surface. So they're not looking, my understanding is that this is not a surface of Venus phenomena. This is up, 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 up in the clouds where it gets a little bit nicer. So the idea is this phosphine creation, alien life or weird chemistry, go with the alien life version of it. So we've got little tiny bits of alien life making the phosphine. I'm happy with that. I don't know how it happens, but I'm happy that this is a thing that could happen. But it's in the clouds. Bacteria in clouds. Okay, I can get my brain around that. You can, if you're small enough and light enough, you'll hang out in the clouds. So I heard from one of the scientists with this report was what they anticipate possibly happening is that the little bacteria making his little phosphine, occasionally the cloud droplets merge together and they rain out of the nice cloud layer. But when you rain out of a nice cloud layer on Venus, you go down the atmosphere, which means you get hotter and hotter. So they think that they actually might dry out completely. Would that be a stress response that something on the Earth does, that literally gets exposed to such heat that it dries out? And then they say, well, of course, once it dries out, it doesn't weigh so much. So it just floats there a little bit until maybe it gets wafted back up to a nicer temperature. Like, do extremophiles here go through such like phenomenally weird, dry? Oh, sorry, you just try for a bit. But don't worry, we'll puff you back to the nice place. Does that happen here?
Yeah, you do get extreme desiccation with certain certain members of these extremophiles, and I suppose the main example of an extremophile, or maybe one of the more well-known extremophiles, would be a bacterium called Deinococcus radiodurans, and this is what's called a polyextremophile, that it's resistant to multiple different types of these extreme stresses. And one of them would be extreme desiccation. So absolutely completely dry out, but they can resist absolute extremes of that. Similar to that, they can resist absolute extremes of ionizing radiation. So up to 15,000 grays of ionizing radiation, which is, I think 5 grays is estimated to be able to kill a human. So that's 3,000-fold tolerance to that ionizing radiation.
And Eamonn, can I cut across there for a second? Can I also join in the Let's Ask Eamonn a lot of questions? So this particular bacterium, whose name I won't even attempt to replicate, do we know if bacteria like that generate phosphine? Does all bacteria generate phosphine? Are there particular ones on Earth, or how common is it for that? So you got to desiccate it, it has to be able to, let's say, survive that, but it's also got to produce phosphine at the same time. That's got to be some part of the life cycle which is relevant to it. So why does it produce phosphine? And if it produces phosphine, does it produce other things that you would expect? So in a sense, the aggregate sum of that, what does that look like? Because actually, I have no idea at the moment what that looks like.
Yeah, I don't know specifically if that particular organism that I mentioned actually produces phosphine. There are certain bacteria that produce phosphine. Normally, they're anaerobic bacteria, so they live in environments where there's no oxygen. And they produce phosphine, as far as I know, from the reduction of phosphorus, and they generate energy from that. But as far as I know, not all bacteria can produce phosphine. I don't know how many or what groups actually do it, but I know it is possible. But I don't know how common it is among, say, bacteria in general as a group.
Yeah, I've got to say, I followed one of the scientists on Twitter, and she's Dr. Phosphine, and she says,
That's great.
we're not the sexy gas that people know about. She said, nobody cares about phosphine until now.
Okay.
And I think that's, I mean, I can remember doing phosphoric acid when I was in secondary school, like, oh yeah, you got to learn your acids, and you know, phosphoric acid, H2SO4, yeah. And apparently you don't need to do much to it to turn it into phosphine, but phosphine's just really nasty. It's used as an insecticide. You use it with your grain to kill off the bugs in the grain because it's a gas you can release. It's toxic. I'm not surprised nobody knows about it. It's nasty stuff.
And I think one of the things interesting if you conversation, I love learning from conversations, even when I'm supposed to be an expert on them. But you know, you have this kind of life cycle, which is very specific, because you have to be able to generate something. Let's imagine we evolve it in the first instance, so it starts off on Venus. We might come back to think about that. Actually, did it originate on Venus, or did it originate on Earth, for example, and make its way to Venus? So, but if you have it there, then I guess the question, you know, we were always taught, you know, this issue of Occam's razor, which says that if two theories equally well explain a phenomenon, then the simpler theory is more likely to be the truth. Now, it's not a principle, it's not a proof, it doesn't necessarily, but there's this kind of underlying sense that when we strip back the way the universe operates, we find that usually the laws that underpin it are relatively straightforward. Now, you can talk about quantum mechanics, and we can have a look at the weirdness of that. We get down to the very small, and maybe we're on that borderline here with some of the interactions at a bacterial level, not at the full cellular level. But it's just like you're kind of thinking, well, do we have a bit of a weird chemistry going on, or do we have this really very complicated life cycle of a life form, not just about generating phosphine? Because when I read it first, I thought, okay, the key thing here is phosphine. And then as I thought a bit more about it, and you said it right now, Francis, and you Eamonn as well, like, but it's not just about that. That's, in a way, that's the easy bit. The phosphine almost is the easy. It's the whole way that you put the whole package together. So I think it's really interesting. I mean, I have no idea. I think in fairness, the scientists in their paper also said, look, there are two possibilities. Well, there's more than two, but it could be effectively some geophysical or geochemical, or it could be something bacteriological, and they've absolutely left open that door. I think it's really interesting that as we look at it more, we're all learning about the difficulties of biology in such an environment, which is as the sweet spot and so on, as if it's going to be simple, but it's going to be complicated, and it's going to be a difficult place to survive.
And
about evolution of these things, by the way, you know, is that a total unfair question, Francis? Sorry.
I'm just, yeah, and not to throw, you know, tons of phosphoric acid or phosphine on everybody, but the quantities of the gas that they detected were tiny. You know, I think that as cool, well, as hot as life on Venus might be, this could also be some funky science that we're trying to detect through our atmosphere, where, I mean, they were using a couple of different types of telescopes. They were using multiple ways of detecting it. But isn't it convenient that there's a spacecraft going past Venus next week? All right. Bepi Colombo, designed to look at Mercury, is doing a swing by Venus in a week's time. Now, its instruments are designed for Mercury. But hey, we got a spacecraft right next to Venus in a week. You know, I understand that the Bepi Colombo team and a couple of the scientists on the phosphine paper got together to say, okay, is there anything you can help tell us? Because it's tiny amounts of gas. Is this a case that we should say, right, hello, everybody going to Mars? Forget it. Come on, this way. We should go to Venus as well.
this is the whole thing that's really interesting to me, because there are books written about Martians and there's so much talk about, I mean, just in terms of like sci-fi kind of thing, right? And there's been this search for evidence of life on Mars for as long as we can remember, right? And I think Venus as well too, but I think that's before we really understood what Venus was actually like. But now with all of the probes and everything that have gone to Mars, it's an interesting transition that it's like, oh, maybe we should think about going back to Venus now and planning more trips there and see what's going on there, because this is interesting. This is a really interesting thing.
Well, it's certainly, Daniel, it's certainly split, or at least maybe not right immediately, but you know, when somebody presents a project to look for life on planet A, somebody will say, well, hold on a minute, there's somebody looking to look for life on planet B, and there's also a valid. So I can just imagine the people who are working on this thinking, oh no, now we kind of got to convince them, not only we look for this planet, but it's more likely we're going to find that planet. And that's a great way for science to operate, because it's inherently competitive. But you're right, it's interesting. In a few weeks, there's almost like, well, this other option, which funding agencies or people are thinking, you know, in the most positive sense, people who are thinking, okay, I want to build a system to detect life. And probably for the most part, they would have been thinking of Mars. They would have been thinking of cold. They would have been thinking about the way also on the surface or maybe subsurface. So they would be maybe drilling down or looking beneath where there would be liquid water and so on. Not really so much in the atmosphere. I mean, we see things like methane in the atmosphere of Mars, and difficult to explain the amount of methane and so on. But it kind of, and again, I'm not an expert on the bacteriological landscape of Mars, but it's certainly all something which, you know, makes the instruments look in one way. Now we've got it's like, I was going to use the word COVID, this airborne thing in the clouds of Venus, which is a whole different suite of instruments. You know, if you go too low, as Francis said, you get fried. So you got to hover there. You know.
Sorry, Niall. Not only fried.
Interesting.
I don't mean to even cut across you, but not just fried, crushed. Pressures on in the atmosphere in Venus, it's like 90 times what it is here. On temperatures are 460 degrees Celsius. I mean, like. It's
just not a good place.
By the way, am I the only one who at some point thought, isn't it amazing that atmospheres weigh stuff? You know, I mean, like the idea that there's 90 times, that's the air above you. There's no magic gravity going on here. That's the way all those molecules in the atmosphere pushing. I just think that's anyway, that was just a bit of an aside, but I remember getting this, whoa, 90 times, where does all this pressure come from? You know, where does all this force come from? But yes, you're right. So it's going to be so. But it also then makes people, for example, like Eamonn, who maybe was thinking, okay, if I was designing an instrument, I'd be thinking this way, and now start to think, well, maybe I need to start thinking. That's exciting. You know, it's challenging, but it's exciting as well. Maybe there's somebody with an approach that they can now pivot quickly towards looking at something which is in a suspended state, probably very low density. You know, so rather than have a big culture on a plate somewhere, you've kind of got a very low density bacteria floating. And how do you detect those? They're low density. I mean, these we get really interesting questions.
Because I mean, it's one thing to think about, you know, the aerogel for going out and getting a sample of a comet, but that's out in outer space. How do you do the equivalent in the clouds of Venus? I mean, back in the mid 80s, there was balloons floating around in Venus and making measurements as they went.
Yep.
Being spacecraft that have landed on Venus. They didn't last very long, but they did land. We have pictures of the surface of Venus. We have measurements through the clouds. We've got radar stuff of Venus. We've got lots of measurements of Venus. But it's really kind of, people went, oh, too extreme, too hot, too nasty. Mars. And I don't know, I can't remember which is the meme with the person looking one way and the other way. I'm like, who's done that for Venus and Mars? Like, you know, human scientists. Oh, you know, and like go.
I know even when I'm talking to kids about planets and stuff, we're talking about finding life in the solar system. Previously, it's always been, oh, we're looking at Mars, haven't seen anything yet. The next possibility may be one of the moons of Jupiter or Saturn.
Yeah.
Where we're looking.
Europa.
Venus was not the option.
And I think that one of the great lessons from this is how wonderful science is, in the sense that, you know, never be utterly definitive when you close the door on something. I mean, it can maybe be fairly definitive. It's a bit like it's that philosophical thing about you can never prove a theory, you can only disprove a theory. And now I'm showing my ignorance of philosophy. There's a lot of ignorance coming out of my conversation tonight. But Amy, can I ask you a question? Because it's just is there a way for us to tell whether life, let's say, that's generating phosphine, let's imagine it's there for a minute, and imagine we can go and we can take samples of it or whatever. So there's no holds barred thing that we can do. Is there any way we can tell whether that originated on Earth or originated elsewhere?
So the phosphine around Venus, is it?
No, the bacteria that generated it. So can we tell a planetary origin?
Wow, that's quite a big question. Yeah, I don't know. How would we determine that? How would we?
Does the DNA look different? For that? I mean, I'm saying this from somebody who really doesn't know the answer, and I don't know if I don't even know if it's a good question, but you know,
I mean,
because that's going to be asked next. You know, can we tell if it comes from? Can we tell if it comes from Earth? Wouldn't that be something you'd want to put into your system?
Yeah, to my mind, like, how do we go to Venus and sample the clouds and take a sample and, you know, bring it back to Earth and culture a bacterial species in the lab and then say definitively that it was absolutely from the cloud, or, you know, maybe there's some contamination on the way back. That's something that I don't know how we would ensure that we sampled it from the cloud specifically in Venus, or whether we contaminated our sample somewhere along the way. I don't know if anybody has actually sampled microbes or tried to sample microbes from space. I know we've sent microbes into space and tried to see how they tolerate it, how long they can survive there. We've shown that some microbes can survive for up to 3 years in space in some experiments on the International Space Station, but the reverse, I'm not so sure.
Well, I'm sorry, did you want to say something about that, Niall?
No, you go ahead. I want to say loads, so you go ahead first.
I want to pivot a little bit, not too far away, but Eleanor back here, my telescope, is not just a prop. She's here because these were detected from telescopes here on Earth. And we actually have a question in the chat here, and from Ellen, who was asked, how do they detect gases? So I'm guessing, how do we detect it from here all the way out there? And yeah, so I'll go with that first, then I have another question after that.
Yeah, well, I don't know who wants to take that one. So, basically, I'll start. But there's something that's really one of the sort of the great discoveries of 19th century science, I guess, and even Isaac Newton sort of indicated it, that you can split light up from being white, from being sort of a normal color, let's say, into different colors. And if you pass white light through a gas in the first instance, what you start to see, it might sort of change its color a little bit. If you look at it a bit more closely, you start to find that particular wavelengths are absorbed by different atoms or different molecules. So actually, what you find is this spectroscopy gives you a unique fingerprint. There can be similarities, but if you look at high enough resolution, it's a unique fingerprint of the light, the color of the light. So, as an example, if you can do the reverse, by the way. If you heat a gas, it will glow, and if you have something that has only one atom in it, let's say hydrogen, for example, you're going to get a red glow from that. And so you can tell by looking at the different colors in the gas. You can do it slightly differently for solids, but you can do it most easily for gases. Then you can actually tell what that species is. And so phosphine would have a unique fingerprint compared to any other molecule in the universe. Here's one thing. When we look out at the universe and we look at stars, we see time and time again all composed of basically the same thing. The fingerprints are replicated right across the universe. And that allows us to make an enormous leap, which is that the hydrogen in your hydrogen-powered car is exactly the same as the hydrogen that's in the most distant galaxy. So the universe is full of stuff, which is particularly the visible universe, that's replicated. That has all sorts of implications as to how, and helps us to understand how the universe likely came into being. But each of those, we can tell that because hydrogen on Earth has the same fingerprint as hydrogen in a distant galaxy, and that fingerprint is different to every other thing. So it's such a powerful tool that we have to be able to tell that. So by looking in the atmosphere of Venus, and sometimes by the way, you don't look with your eyes, you have to look at slightly different wavelengths, but the principle is the same. So you might look at infrared, you might look at millimeter, but all of these are part of what we call the electromagnetic spectrum. So the mechanism, so all of this is effectively light traveling at the speed of light. Some of it's visible to our eyes, so by definition we call it visible, some of it isn't. And the process by which you detect it can be a bit different. So our eyes can't detect millimeter wave just because
the ALMA detection is millimeter wave, isn't it?
It is, yeah.
Certainly, I heard one of the project scientists saying, it'll be great when COVID is finished and ALMA is working again, because it's one of the telescopes that's currently shut down.
Yeah.
I think a lot of the telescopes, a lot of places, a lot of places are just currently not working. So they're going, the people there at ALMA, they know what they're doing. They know what they're looking at. They know what they've detected. They've allowed for the atmosphere. But unfortunately, everybody's on break right now.
Yeah, I know. And it's a really good point, Francis, because if you look at radio telescopes like ALMA, which are, a very high altitudes in super dry deserts where the Earth atmosphere has the minimum chance to absorb with the radiation. It's not zero, but you minimize it. And that's, by the way, why you put observatories up high. You always do that to get above as much of the atmosphere as possible.
Like on top of a tower at a castle?
Like on top of a tower of a castle, yeah. And a little bit taller would be even better, but I'm not sure we can really structurally justify making Blackrock Castle Observatory taller. But molecules actually are very difficult to detect in optical. So actually, usually the bigger and the more complicated a molecule is, the more you're likely to find it at longer wavelengths than at shorter wavelengths. So you can detect the constituents of it. So a molecule is going to have a series of atoms of it. If you want to detect the entire molecule, it's like if you want to detect the entire car, you need to look at one wavelength. If you want to detect the different bits of the car, you look at a different wavelength. And so big molecules require totally different technologies to detect, but we've become good at that, and we've learned that it works really well. And it's a very impressive success of the human race, I have to say, that we sit on this tiny ball, and we can even right now be saying, there's phosphine in the atmosphere of Venus. That's an incredible statement. If you unlock it another way, that's amazing, because without actually ever having gone to Venus and detected phosphine there, we can still say it's impressive. And I think we should give ourselves a clap on the back as a species, and then say, stop acting the maggot with climate change.
No,
and get on with being good.
Go ahead,
sorry,
Francis.
I know you're going. Just talking about the detecting and something. I picked up again from one of the project scientists that this phosphine may well, and whatever life form possibly is using the phosphine, that there could also be sulfur chemistry being involved. But then they went and spoke to the people who are good at detecting sulfur, who said, yeah, hard to detect. Go look at something else. So I was going to go back to Eamonn. Does sulfur go in living things? I got to say here, the biology classes I've been in, I've been very few in number. So do you get sulfur regularly in living stuff? Is stuff quite happy to take in sulfur?
Yeah.
It's pongy, right?
It's
yellow stuff.
I suppose if we kind of go back to kind of first principles on the composition of pretty much every organism on Earth, you can break them down into, 98% made up of 6 elements of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And there's obviously other trace elements involved in that, but all the major biomolecules in every organism on Earth are primarily composed of those 6 elements in different combinations. Sulfur to a lesser amount. Obviously, carbon would be the main one. We're all carbon-based organisms, but sulfur is important, particularly in proteins. But if we're talking about metabolism and using sulfur as a way to generate energy, there are organisms that use sulfur to generate energy.
Okay, cool.
And particularly extremophiles actually use sulfur to generate energy. So some extremophiles, you know, they can oxidize sulfur, or they can oxidize other things like iron or hydrogen, and they can use that then to generate energy for themselves. Again, among the extremophiles, a lot of them actually, I suppose this kind of links back to maybe the conditions in the clouds in Venus, that there's a very low pH in those clouds. There's an anaerobic environment. And a lot of these extremophiles generate sulfuric acid from sulfur as part of their metabolism. And I think sulfuric acid is a component
all over Venus. Like, I'm not sure that you'd be able to spot the sulfuric acid from the extremophile compared to just the sulfuric acid.
Yeah, no shortage there.
Yeah, it's kind of nasty, but I just thought it was an interesting thing that then the sulfur detection was the reason they kind of went, oh no, okay, we could do all the maths and we could work it out and we could figure out how sulfur is involved, but we're actually not going to be able to spot it, I think was their issue. But it's interesting to know that you can get your bugs with your sulfur in them.
Sure, yeah. And I mean, pretty much any element, there's probably some more microorganism that can use it in some way to generate energy for itself. The adaptability of microorganisms is incredible, really, using things like sulfur to generate energy for themselves.
Oh, cool.
Yeah,
it's cool.
That's a good word for it.
I've got
maybe.
Sorry, Niall. So I got another question here in the chat that says, are there other good reasons to go to Venus that might help justify missions to search for more evidence of life?
Life? I'm sorry, that's enough. Okay, there's currently a couple of proposed missions that people have put forward that have not yet been approved, and there's 2 to Venus. Okay, NASA have 2 under consideration, and they've come and said, oh, actually, this might put things a little higher up the list. Okay, so I suppose it's, do we need to know if there's life elsewhere? Is that something that's important to us? If you're not that bothered, then you don't need to worry about it. But if you've ever wondered, are we it? Having 2 planets with life in our little corner of our solar system, that blows it open for what else is out there. Like, 2 in one little place. I mean, 1, obviously we're here, but 2?
Both Francis, but that goes back to our earlier question about how we figure out whether actually they had a common origin or independent. Okay,
true. Yeah, you were saying that.
Yeah, so I mean, I think this is why I'm trying to understand from a physicist's perspective, because sort of from a ballistic perspective, something whacks into the Earth, throws material into space, it's going to naturally move sunward, some of it. Venus is a small target in a very big solar system, but it's a non-zero possibility that material gets transferred. I mean, we know, obviously, that you can find meteorites from Mars in Antarctica, and these are found quite regularly. So once you give any, and again, Eamonn can maybe come in here, but so my understanding is that the earliest life in the on the Earth has a extremely long, you notice I'm using a bit of a vague term here because I realize I don't know what the number is, but it's got an extremely long time scale. So extremely long time scales, early Earth with lots of early-ish Earth with more bombardments, because we know the early solar system had a lot more collisions, ability for material to be thrown out into space. So I agree with you. if we go to Venus and we find that we'll come back to Eamonn in a second, but we find that something, then we got to say, well, okay, where did it come from? Because the difference between it all, 1 and 2, is enormous. It's absolutely enormous. So
life on 2 planets from the same planet doesn't have that same knock-on as independently the spark of life, whatever created the life. You know, is it a case that, you know, you get the right chemicals, you get life. And if that's the case, there's a lot of life out there. But if you got to have the right chemicals and
something,
you know, what's the something? Is it whatever is driving those chemicals to get together to reproduce themselves in a way that we would call life? You know, that, you know, a candle flame isn't alive.
A friend of mine used to say, well, he would still say, the really difficult bit is the bit between, you know, all these atoms and so on, sticking them together to make even the simplest life. That's the difficult bit. The evolution actually is relatively straightforward.
Yeah, it's straightforward.
Eamonn, how difficult is it? I know we don't know how life started, unless you know, this is the last few minutes. But you know, from a biologist side,
there's a very famous experiment of stick the stuff in a jar and zap it,
and nothing.
You don't get life. You get more complicated molecules, but you don't get life.
Yeah, you can build complicated molecules, but like Eamonn, so do Extremophiles.
How do we get from
move that on? Yeah.
That's
Please help us. We're clearly struggling.
What's in the gap? What's in the gap besides our brains? Our brains are in the gap with nothing. So what's in that gap between there's life?
Again, it's a big question. Am I about to like solve the biggest mystery?
I'm sorry, this is what happens when you put.
We get a lot of views. We get a lot of views.
We've solved the mystery of life.
Yeah, I think it's kind of accepted that, you know, all these elements existed in this kind of primordial soup, and something happened. You know, maybe a lightning bolt or something that just magically bonded them together to make some sort of primitive molecule that could replicate itself. I think kind of the consensus at the moment, and I'm open to correction on this, that possibly RNA was the original molecule of life. It's kind of a self-replicating molecule made up of nucleotides. So we have DNA, which is then transcribed into an intermediary molecule of RNA, and then that's ultimately made into protein for the cell. So I think the kind of the prevailing thought on that is that RNA was possibly the original molecule. It has the ability to self-replicate itself, and then eventually it found the ability to you know, maybe enclose itself in some sort of a membrane, which eventually developed into a cell.
So would RNA be considered alive?
No, I would say no, because it's.
So I'm sorry, we're still over here.
Yeah, we're way away from where we need to be.
This, I gotta say, all of this is so interesting, but it's why I went into physics. It's complicated. It's complicated.
And physics is simple.
Physics is easy by comparison. Oh my goodness, you know this, Niall. Physics is straightforward.
Oh, don't give the biologists any opportunity to think that they've got the upper hand, Francis.
Oh my God, the biology is just so many enormous questions and so many.
Speaking of which, going back to the question that was being asked about Venus, other than, and you've correctly pointed out that life is a critical, but are there other things that knowing more about Venus? So, for example, before the phosphine was detected, why would we bother to go to Venus? You know, so what is it about Venus that helps us to understand? So, I mean, I guess, you know, one of the things we're always trying to understand, and you can decide on a value of this in absolute terms, but we try to understand how did our solar system evolve. And, you know, the early model that we had of the solar system, which is the sun at the middle, which is going to be the case. The planets form around it through sort of collisions or aggregations, so sort of sticking together. and then gravity starts to pull stuff, and gravity naturally will pull stuff into spheres if you make them large enough, and so planets build. And because the sun is hot and it has a wind, it blows the lighter gases out, so you end up with the very lighter, low density planets further out, and the higher density planets, the rocky planets, further in. But even in the last few years, we've seen a couple of things. Since we've discovered other exoplanet systems, this isn't always the case at all. Our solar system currently remains unique in the distribution. Now, one doesn't necessarily read too much into unique, because we've discovered only about 5,000 other planetary systems, so it's still relatively small numbers. But we see lots of them where the large planets are close in. There may or may not be small planets. So that has got us thinking about the fact that Jupiter probably was much closer in and moved out, and Venus probably moved positions, potentially even with the Earth at some point early on in the formation of the solar system. So going back to Venus, or looking at Venus rather in more detail, helps us understand something about the early formation of the solar system. Now, you can decide separately whether you think that's really worth knowing or not. It's not as fundamental a question, and it doesn't have the same psychological impact as the knowing about life, but it will tell us something about how our solar system evolved. And I guess that, given that's where we live, possibly a good thing to know.
Can I put a vote in also for understanding a runaway greenhouse effect?
Yes.
What happens when your planet gets a little bit too much gas and gets a little bit warmer, and then gets a little bit more gas and maybe gets a little bit more warmer? I was doing some stuff last week with second level students about albedo modification of the Earth, about what happens if you change how shiny we are.
Albedo, Francis, albedo. What's albedo?
Albedo, shininess. How shiny are you? And I said, our Earth is pretty shiny.
Paint your roof white, right, Francis?
Paint your roof white.
Paint the mountaintops
our Earth is
white.
pretty shiny. We shine away some of the sunlight that comes onto us. I said, Venus shines way more, but it has a much thicker greenhouse effect. It has thick clouds, and so it retains, whatever radiation makes it to a surface pretty much stays put. And I said, no, in our planet, if we want to limit our greenhouse effect problem, what if we make our planet a little shinier? Make a few more clouds. And I said, but one of the problems we have is if you warm up and you melt your ice caps, then it's not as shiny. So you warm up and you melt your ice caps and it's not as shiny. So you warm up some more and you melt your ice cap, and that's your runaway greenhouse effect. And hey, we got a planet over there that's already done the runaway greenhouse effect. There's another reason to go study Venus.
And you know what? Even the fact that we know this already tells us anybody who doubts, not in a negative sense, but anybody who, for good scientific reasons, for example, could be that who have modeled something that says, well, the planet will re-equilibrate. It will, but it may re-equilibrate at 400 degrees centigrade surface temperature, which really isn't a great equilibrium. No. I mean, how many bacteria? Are there any things can live at 400 degrees, Eamonn, for an extended period of time?
Can I piggyback on that conversation as well for Eamonn? Because from my understanding, and like I said, I'm not a huge I don't know that much about it, but don't we live out of equilibrium from our environment? So is that something that if we are living in a situation where we as organisms that are living, as we categorize it here on Earth, but we're living in an environment that's out of equilibrium, are we looking for life on other planets that is also the same way we are, where it's not maybe at equilibrium, or are they also going to be not like us and be at equilibrium with their environment? Does that question make any sense?
No. Sorry, I'm lost. I'm lost.
You'll always have like a set of optimal conditions for life for particular organisms, and there'll be a range of variation that each organism can exist in between, and there'll be limits to that as well. As humans, I'd say our limits are quite limited compared to things like extremophiles or bacteria. They're much more adaptable and much more resilient to different types of physiological stresses than we are. But I suppose we as a species, we're one species. So even though we are quite diverse and quite different individually, we're still just one species. Whereas if you talk about bacteria, there's thousands of different species, or tens of thousands, and each of those are vastly different at the genetic level and the physiological level. So it's not surprising, I suppose, in a way, that you see that kind of extreme difference in the types of physiological stresses that they can cope with, because there's just a huge diversity of species, huge diversity at the physiological level and the genetic level. Niall, your question was?
Yeah, I was curious, Eamonn, about what is sort of the extreme temperatures that we know. So I'm going to use the word bacteria. I hope that's the right term, but can live on the Earth. What do we know is already a definite limit. Now maybe it could be more, but
I think it's something that's quite dynamic, that it changes quite often. That the more we kind of explore these extreme environments, the more we see expansion of the upper and lower limits of those extremes. I think probably somewhere in the range of -20, -25 degrees up to somewhere in the region of 120, 130 degrees Celsius.
Yeah, I've heard quoted before, hot springs, living in hot spring.
Mm-hmm.
And the quote I have that's coming to me is, the temperature at which your dentist sterilizes the equipment, which just makes me just... Please, dentist.
Even higher, Francis.
Do other... Oh my God, no, I don't want to hear this. I want to know that my dentist's equipment is clean.
Yeah, we would sterilize those things in an autoclave at 121 degrees for 15 minutes.
And that's not enough.
It's enough to kill pretty much everything.
I don't want to hear pretty much everything.
But something from a geothermal vent is not going to be on your dentist's drill, so you
good,
and it's not going to make you sick either.
Good, excellent. This I want to know.
You're safe enough. You're safe enough. Yeah. But that's kind of they're kind of the extremes of temperature for. Some organisms can survive at that, other ones can thrive and kind of grow at those temperatures. There are...
Oh, no, I'm sorry. There's a difference between surviving and thriving. They're thriving at that temperature?
Some can thrive maybe up to 110 degrees Celsius.
No.
Certainly survive up to 120, 130 degrees Celsius.
And there's how many species of these?
Oh, tens of thousands.
Oh, yeah, right. Physics, bring me back to the physics.
You don't need to be afraid of these, Francis. The majority of microorganisms that exist are either beneficial or do no harm to us. It's only
good.
Very
Tell me these good words.
Minority that get a bad rep, I suppose, and particularly in current times we have, we're kind of
like the flesh-eating bug type.
Oversensitized to microorganisms and the harm they can do.
Yeah, I know. I do understand the people who do the bio yogurt and tell you about the friendly bacteria. Mm-hmm. The whole fact that the bacteria are friendly in my yogurt, reassure me.
Yeah, that's good.
Yeah. Possibly, I always look on this from an average life expectancy type of approach, and despite whatever on the average, and obviously by definition, there's a distribution and people different ages, but. We seem to be able to coexist with most of these nasties or whatever, either because we don't come into contact with them, like as Eamonn said, like how many of us go down to hydrothermal vents on the ocean floor? Probably not many of us, and they don't seem to want to be very mobile. But what it does suggest to me, going back to part of the question of Venus, is that you still have you're still looking at a surface which is likely to be sanitized. I mean, probably, I was trying to imagine even at 400 degrees centigrade, that's going to start to dissociate lots of molecules, lots of stuff is going to start to break up at that temperature, I would have thought anyway, so you would have difficulty in just purely existing, irrespective of whether it's a life form or not. But Eamonn, you've done, we Danielle mentioned at the beginning a little bit of this whole area that I know one of your colleagues, and I know I did a bit with them as well, talk about panspermia and the idea of purposefully seeding life elsewhere. So a couple of questions. I mean, I think I kind of know the answer to the first one, in the sense of seeding life in Venus, unless we do it in the atmosphere. But what about other other places. Can we look to transfer life from this planet to other places in a way which will be more likely to survive? What's the kind of current thinking on that? That seems to me to be an area that's fascinating.
Yeah, it's quite an interesting area. I think, like you say, if you're to fire stuff onto Venus, that pretty much nothing would survive on the surface. Maybe Mars would be more of a hospitable environment, even with its, not ideal, but perhaps you could engineer or design specific microbes that would be able to survive in that environment.
So what does that mean? Because I'm always fascinated. So casually you say design or engineer a microbe. So in general terms, a physicist might be able to understand what is involved in that. Because it sounds like you put together molecules in a different way than nature put them together, let's say. So
I guess where you would start would be what are the conditions on the planet you want to send this potential microbe to. So say, for example, Mars, you've got high carbon dioxide in the atmosphere, and you've got certain chemicals in the Martian soil and all that. So what you would do is, I suppose you would look on Earth and see, is there microorganisms that can potentially encode proteins or have the ability to, maybe detoxify certain chemicals that might be in the Martian soil, or can they use the carbon dioxide in the atmosphere and convert that into more usable forms for other organisms, or for maybe growing plants or vegetables or things like that. So what you would do is, I suppose, you look at things at the DNA level, which are basically instructions for life, and can you modify those instructions to your own devices for what you want to do on that particular planet. So say, for example, you've got bacteria called cyanobacteria that are a very kind of unique group of bacteria that live on Earth. You find them on the surfaces of the oceans, and their kind of unique ability is to use sunlight to convert sunlight into chemical energy for themselves. So in the process of that, they're similar to plants, the way plants use chlorophyll to convert sunlight into chemical energy. These cyanobacteria are kind of similar in that way, that they use sunlight and they convert that photo energy into chemical energy and produce sugars or carbohydrates, and they release oxygen as part of that. So kind of, I suppose, if you had kind of a grand plan to kind of oxygenate Mars, you would have lots of these cyanobacteria that would be taking in this sunlight and converting that into oxygen, which would be released into the atmosphere. And that's kind of similar to what's thought to have happened on early Earth, where these cyanobacteria were the original propagators of oxygen on Earth.
My understanding
plants get all the credit for photosynthesis, but it's actually cyanobacteria are the real champions of that.
Yeah, you say that with emotion, Eamonn. Defending the bacteria against the nasty plants.
Absolutely.
But my understanding then is oxygen is quite a reactive molecule, and therefore doesn't remain in an atmosphere particularly. Like, it reacts with lots of things. So if you see the presence of ongoing oxygen, it's an indicator, another one of these indicators of a potential life. I mean, we've already talked about possible other, things that generate phosphine. So, but because going back to spectroscopy as well, and how would we look for signatures of life? So, have I got that right about the oxygen being, something that really is introduced into a planet largely by life, or am I wrong on that?
That's my understanding of how it happened on Earth is that these primitive life forms developed eventually into these cyanobacteria, and they were primarily responsible for creating this oxygen atmosphere on Earth, or increasing the amount of oxygen in the atmosphere on Earth.
But hang on a sec. Our phosphine bugs are in an anaerobic environment, so no oxygen. So there's still happy life things to which oxygen is the bad guy.
Absolutely, yeah.
Good guy for us. So did they develop in parallel? Was one around and then the oxygen ones took off and these guys went, okay, I'll just stay over here where there's no oxygen. So it's guts, isn't it?
I think that's essentially it, you know. Originally, you would have had these anaerobic organisms, which still exist, you know, that
Yeah.
the early conditions on Earth would have been absolutely no oxygen. So the first life forms would have been completely anaerobic. And then over time, you know, you would have had these organisms that utilize oxygen or require oxygen for growth, or they produce oxygen as part of their metabolism, would have developed, and eventually you would have some sort of maybe a flattening out where they all exist together, but in different kind of environmental niches. So, you know, we have lots of anaerobic organisms that still exist, you know, in these deep sediments in your gastrointestinal tract, which is predominantly an anaerobic environment. The majority of organisms, microorganisms that live in your intestine are anaerobic, and oxygen is toxic to them still, even though these were probably the earliest organisms that existed on Earth.
Am I right, Eamonn, in that?
And we need them, don't we?
Oxygen does for you is it allows you to build bigger and more complicated organisms.
Biomolecules and organisms, yeah. So, yeah, and again, you know, in cellular respiration, you know, you're a lot of organisms use oxygen as an electron acceptor to kind of generate energy or generate ATP, which is the primary energy molecule within cells and within the majority of organisms on Earth. Excuse me. So oxygen is hugely important for us as humans to generate ATP, for bacteria that can use oxygen to generate energy. Those anaerobic organisms that don't like oxygen, they use different electron acceptors in place of oxygen. So, you know, bacteria find a way, you know, in the presence or absence.
I'm sorry, the takeaway, bacteria find a way. Oh my God, no.
Just in terms of evolution, Eamonn, and apologies for this again barrage, but does that mean that anaerobic life forms or anaerobic organisms have less potential to evolve into large, complicated structures? Does oxygen play a cue? I'm obviously thinking go back to Venus again, and could those bacteria, you know, what would be our guess on whether they could ultimately evolve into something that could build machines that would...
They're in the clouds. No, they're in the clouds. It's not going to happen.
Yeah.
As soon as they get busy, down they go, dry out, they're dead.
Well, apparently they're not dead. That's the thing. They get reset.
Okay, but they're not.
Down,
they're
they
not.
get dried out. They go back up.
Something with hands and a brain.
Yeah, but
can
we know
they evolve?
We know we've got organisms here on Earth that can dry out and then be rehydrated. So I don't know if that doesn't seem like an issue to me if they come down.
But every single time you get more of these bugs together, they sink.
Yeah, it's still out with the question.
Cloud-based life.
It's
okay.
The question: can they evolve? Does oxygen, the lack of oxygen, frustrate the evolution?
And gravity is frustrating them.
The lack of oxygen is not going to affect their ability to evolve. The lack of oxygen for them is just the way they exist. You know, they can still evolve.
Do we have anything on Earth? I guess the question then, Eamonn, that we would call highly complex. Now, I don't know what the definition of that is in this context, and that is anaerobic.
You mean more complex than, say, a bacterial cell that's completely
something
anaerobic?
You might talk to or read a book or pat on the head.
I don't think so.
Something useful, and that doesn't frighten Francis.
My brain is boggling. I'm like, okay, we're
if we look
Niall wants a pet anaerobic. He wants an anaerobic pet. Okay, he wants something to look at him and go, woof woof woof. Niall, I'm your anaerobic pet. No,
it might sound different.
It's that way.
But and it is always a serious question because it opens up a different parameter space when we look for evolved life forms in the universe and where we would, as distinct, so I'm just curious.
I don't know, it almost sounds like we're getting into that whole science fiction world of utterly, totally different life with a different chemical structure and arrangement. And I think that's what you're getting at. If we take the oxygen out of it, how likely and viable is it that you can do complex everythings with no oxygen? I know. I mean, this is everything you just said. Given that Eamonn has told us, right, we've got our 7 major parts. If we take away the oxygen, does the rest fall apart?
No.
No, there we go. So yes, you can have your anaerobic pet.
Yeah, we have these as there's different groups of bacteria. Some of them cannot grow, absolutely cannot live without oxygen. Other ones absolutely cannot survive in the presence of oxygen because it's completely toxic to them. Other ones need a specific range of oxygen between 2 and 10%. So there's a huge there's a huge variation in oxygen requirements in microorganisms. So pretty much bacteria, microorganisms cater for all levels of oxygen.
Okay, but just to press you on this, but they're still bacteria. They haven't evolved beyond the level of bacteria. They don't build bridges. They don't go and look out in the universe. And so I understand, can you have sentient beings then, let's say, who understand that they exist, who maybe have emotions and so on, built, at least in principle? Well, 2 questions. Do we have anything on the Earth that does that, or does everything at that level be aerobic? And is there anything that we know fundamentally prevents that from happening? Because that does mean that we can look in locations in the universe. Now, oxygen is very common in the universe. One of the reasons it's so common. So I'm fully aware of the limitations even of my question, because oxygen is made early on in even solar type stars. Stars like the sun have capabilities of making oxygen under what they call the CNO cycle. Larger stars will make that. So oxygen is a very common molecule in the universe. So it would be difficult to imagine a planet where somehow the oxygen had been extracted in the formation process. But just because we're having this interesting discussion, if we could do that, is there any sense of whether or not there is a limitation to what you could build with anaerobics? And I don't want them just to be a bacterium. I want them to be...
If you're talking about a living, breathing, standing up person type organism.
Yeah, they can be lazy and lie down if they want, but they need
I don't see why not. If
okay,
with the amount of galaxies and planets we have, maybe there's an alternative
anaerobic
universe where it's kind of the opposite to what we have. Yeah,
interesting.
Yeah.
But so in agreement. Sorry, are we in agreement that this is a biosignature? Because I've seen a little bit of a debate as to this could be possibly there based on other things that are not generated in a bio way. So are we saying here that we think that the phosphine is coming from something that is alive?
I think it's more interesting to take that view. But I think if your choice is between weird biology, weird chemistry, I think the chemistry wins.
Okay.
I love the idea of weird biology, but it's a tiny detection. I would be much happier with more robust work and somebody else detecting it. Right? It's one team. It's the phosphine person who wrote a paper about phosphine as a biodetector, and then another team were out looking for phosphine. They got together, and then there's a chemist who's done all the maths and the thermodynamics and the energy, and said, no, you can't do that. But we're saying, okay, let's get a totally new life form in a weird environment where we're not expecting anything, or it could be some chemistry. I'm going to go with the chemistry.
So you're not sold on this, Frances?
I'm not sold. Put an X in my square.
And anyone else do we have, Niall, do you have an opinion on this?
I'm not as brave as Frances, I think, would be one thing. For me, there's 2 questions. One is to confirm that this is coming from a biological source, and then second, to determine the origin of that biological source. So I think it's worth pursuing.
Yeah.
Well, you know, you're saying, by the way, Franz, I know you would never, you know, say the opposite. So I think it's sufficiently intriguing, but we would probably start by, and I'm guessing, and this is just a guess, but a bit like cold fusion.
I remember cold fusion.
Yeah, and sadly, so do I. So there's an age thing here going on, Francis, maybe. But the cold fusion was interesting, you know, for maybe a relatively short period of time, but the implications of it, that you actually fuse nuclei together at room temperature or very normal temperatures, had enormous implications. So people rightly said, wow, that's amazing. There could be some physics we don't understand going on here. So let's have a look at it. So they did, and they couldn't replicate the experiment. The phosphine is definitely there. I think nobody's in any doubt about that. It's a superb piece of work on detection of phosphine. But my understanding, just to say to your question, that we're probably limited what we can do by staying on the Earth and observing Venus. I think we're probably going to have to go there and do other things. And that's coming back to, now we start thinking, okay, what would those two experiment missions that Francis mentioned, could they be changed slightly so that if you did go to all that complication of putting something in the atmosphere of Venus, that it would now maybe do something a bit different? And just as a final point on that, Danielle, it's actually really difficult to go and land on Venus. Or go into the atmosphere. It's actually easier now. Nothing is easy, but it's easier to go to Mars. The sun is this huge, you know, thing that's sucking you past Venus. So to actually fall towards Venus and not go past it is really difficult. So you
fall
often
and stop where you want to go.
Yeah. So it actually becomes a very complicated mission to do as well. I mean,
but the Russians have done it so well. The Russians have done a great job. In the 70s, they were going.
I was going to say, and that was a while back, and technology has really advanced since then.
Yeah.
So interesting to see how this.
The one thing that hasn't changed is gravity. So gravity and the laws that we've known the laws that you need to know in order to move spacecraft around really since Isaac Newton. I mean, small variations, but really the Newton's laws, Newtonian physics is sufficient to do most things with spacecraft, especially if you can make small adjustments en route and so on. So I think it's fascinating. I think it absolutely needs more analysis, but it's a lot more analysis, I think, before it becomes really, really interesting, because it has to be a unique origin for it as well. Transfer, it's interesting, but it's kind of something that you can see how it might happen. And going back to some of Eamonn's comments of extremophiles and that, you know, and anaerobic stuff that can you know, go between here and Venus in a couple of months or whatever. It doesn't seem to be something that is impossible just using Earth-based.
Okay, so I'm a there. You're a
kind of in between.
He's
I'm gonna give us more funding for more research. So
he's like a hashtag watch this space kind of thing.
Yes.
Yeah.
So Eamonn, I think I'll give you the final say and seal the deal here. You want to be the tiebreaker? Eamonn.
Yeah, I mean, for me, I suppose this kind of alien life concept. I mean, when I think of that, or when that phrase comes to mind, I automatically think of microbes, and I'm biased because I'm a microbiologist. So my brain won't stretch to maybe, you know, kind of a intelligent life form, you know, walking around the planet. But, you know, is it possible that there is kind of alien life in a microbial form? Yeah, I think so. And Francis mentioned the conditions in the clouds of Venus compared to the surface, you know, and the clouds of Venus seem to be quite balmy conditions to what some of the extremophiles on Earth actually encounter, you know. So, you know,
they're so thick, they got everything.
Yeah, and they've got the organic molecules that could support life. Again, it goes back to the point Francis made, you know, how do they stay in the cloud? Do they drop out, or you know, how are they maintained? I don't know the answer to that. So I'd be hopeful that, you know, I think it'd be really cool if we did find some sort of life somewhere.
I'm with you on that. I'm with you
life
on
we will
that.
find, I think, will be microbial rather than some guy walking around.
That you
waving
can
at us.
pat on the head.
Yeah,
Yeah.
exactly.
I don't think you're going to get this, Niall.
Yeah, but I'm the only one of the three of us, or indeed the four of us, but the three of us that have been asked to make a thing who's going to get funded to continue the research. You guys are just, so, I'm happy.
I'm sitting actually between, I actually don't care either way if it's life or not life, because I like both of those possibilities. I think the outcome from either of those is very interesting, and either side could get more funding to do more research and see more things go to Venus in terms of missions. And so I think it's a very interesting time. And I'm going to go back to the whole thing of like, we've been looking at Mars for so much in terms of missions and things. So let's look at our other neighbor and see what's going on over there. But Frances, she's a Venus fan, so
I'm a Venus fan. I this morning I looked out of my window and went, "Good morning, Venus. You're gorgeous."
Yeah, you got Mars in the evening, Frances. You got Venus.
Got Mars in the evening. I got Jupiter and Saturn behind me, and I've got a perfect view of Venus every morning. It's just beautiful.
I'll tell you what you don't talk about with Frances is Mercury, but that's a talk for another time.
Pepe Colombo.
So I just,
Mercury.
Actually, you know what?
Mercury is actually cooler than Venus, even though it's so much closer.
Oh, Niall, no. Okay, we can't open that can of worms because
no, don't go there.
Frances will be very upset about
it.
Don't go there. Don't go there.
For anybody who's watching, Frances has had a very hard time tracking down Mercury and has only seen it very few times in her entire life. I got to see it last year though, so I was very excited, and that's all that matters.
I am 12 times in 40 years of looking.
That's more than I thought.
6 of them were the same week. Because I was looking for a comet that I never saw. But
this really sounds to me like a situation where you say, "My name is Frances, and I haven't been able to see Mercury."
I know.
It's that type of admission.
I deeply need some therapeutic support here. And
I just remembered I saw it twice last year.
Oh, thanks so much.
Okay,
are we done?
I saw a crescent Mercury from an observatory in Zurich, and I saw the transit happen as well. So I've only been looking for it for a couple of years. And that wasn't in the same week either. We're not even the same month. But
You're okay.
I have to work with Frances tomorrow, so I'm just going to be very... But I just wanted to say thank you so much to everyone for your time and your expertise and for having this lovely chat. I had a great time. I hope you guys, did you have fun?
I'm worried about my dentist.
Oh,
don't worry, Frances.
I'll think about that, the cleaning of teeth and tools and things. But thanks everyone for that's been watching on the live stream. Thank you for all of your questions, and I had a fantastic time. It was a great way to celebrate Space Week. So thank you so much for hanging out with us tonight, and we will see you in the next one. Make sure you subscribe to the channel, and then you'll get notified when we do another live stream. So have a good evening. Happy Space Week.
Good night, everyone.